In this video, we are going to examine the distance formula, the circle formula, and an ellipse formula. These gear specifically towards the generating geometric properties with equation standards. So let's get started on our work. Where does the distance formula come from? I know you've done it in earlier classes, so mostly this is checking, do you still remember where the distance formula comes from? The distance formula we're referring to is the distance between 2 points in the coordinate plane, which is this thing. Where does this come from? Right, here's the quick version. It comes from the Pythagorean Theorem. Consider this. We could have a point right here, x1, y1. And we could have a point over here, have x2, y2. What is the distance in between those 2 points? As I'm sure you recall, the shortest distance between any 2 points is the straight line. So essentially, we're saying what is the length of this line segment. That's what the distance formula does for us. I'd like to make a couple of observations. And these are, of course, observations that we've seen a couple times in class. We can fill this part in right here. What length is that? As we noted previously, this would come from taking the, I'm going to change the color to blue there. You take the right x-coordinate, subtract off the left x-coordinate, and you would actually get the distance for the run. Similarly, we saw that this component, the rise, we could take y2 minus y1, and we've seen this picture before when we were creating the equation of slope, when we were creating the equation of a line. We've seen the picture before. Well, all we're doing now is taking an additional interpretation behind it. What kind of a triangle is this? Absolutely, we've got a right triangle. And one of the things that you've learned about right triangles, you have the Pythagorean Theorem. Legs squared plus legs squared equals the hypotenuse squared. Well, looking at this particular thing, I'd like to rewrite it so that I have hypotenuse squared equals leg squared plus leg squared, just using the symmetric property. Well, please observe the first leg is the run, x2 minus x1 squared. The second leg is y2 minus y1. That's the rise squared. And our hypotenuse is the thing that we were actually trying to get. It is the distance squared. Well, ask you to take a look at this and tell me what would you need to do to create that distance formula. Absolutely, Alex, we'll just take the square root. Taking the square root of both sides, we have exactly what we wanted. Distance is equal to the square root of run squared plus rise squared, because rise and run are just the legs of our right triangle. You look like you have a question, Vernon. Okay, now that Ryan's worked his confusion out, please note the important observation. The distance formula is just the Pythagorean theorem. All we've done is to create a right triangle in the coordinate plane, rewrite it algebraically to fit the specific x and y coordinates, but it is the Pythagorean theorem rewritten in a different way. Get your graphing calculators out. We want to find the point on y equals 3x plus 4, which is closest to the origin. So, understanding what this is telling us, we would have the point, the graph, 1, 2, 3, 4. Okay, we could create this line, and of all the possible points on this line, which one is closest to the origin? Now, of course, we know that we could go straight up and get a distance of 4. We know that we could go down here and get a distance clearly larger than 4, and up here clearly larger than 4. Of all the possible points on the line, where is the one location that is closest to the origin? Well, graphically, we should look at it and say, here. But how are we going to get that point? What are the exact or precise locations for that particular point? Well, the main reason we grabbed the calculator is so we could think of this. If we want to have the closest distance, that means it's the smallest distance, which should let us know that we can use the minimum feature of our calculator. We just have to create an equation. Well, why not use, if we want to know distance, we'll use the distance formula. The only thing that we have to figure out is what do we type in? Okay, so what are the x and y coordinates that we're looking for? Well, we're looking for this point, xy. So we can put those into our formula. Distance. What's the other point we're looking for? Looking for distance from the origin, which of course is the point 0, 0. So we can use another point, x is 0, y is 0. And so we wind up with this simplified version, the distance formula. Hey, check it out. Isn't this looking a lot like Pythagorean Theorem again? Well, one of the things that we should also observe, we know the value of y. Tiny. We have an equation. Y is equal to 3x plus 4, so we can make that substitution. This isn't just the point xy. Because it's on the line, it has to be of this format. We'll make that substitution and say distance is equal to the square root of x squared plus y squared. And we now have something that we can put into our calculator. Of course, we know that the calculator does not accept equations of the form d equals. It'll actually be y equals. but this is what we can put into our calculator. So grab your calculators and do it. Switch this over. Come on. Switch. Oh, man. Forgot to switch that over to this. And Y. So we will create our graph. The square root of x squared plus 3x plus 4 squared. And we'll use the standard window. And so here is a parabola. Something that, anyways, it looks very similar to a parabola. And we want to know where it reaches its minimum, because this is a distance function. If we were to use the trace, this is telling us at the point where x is equal to 0, it is a distance of 4 away from the origin. Scrolling over, at a x value of negative 0.15, it is a distance of 3.55 away from the origin, and so on and so forth. We need to figure out where it bottoms out, and so we'll have to use the calculator's minimum feature, and take our left bound, take the right bound, put a guess in the middle, and here we have our result. Rounding to 3 significant digits, when x is negative 1.20, we obtain the minimum distance 1.26. Thus, answer the question, find the point which is closest to the origin. We had an x value of 1.2, and the y value on that line, 3 times 1.2, I'm sorry, negative 1.2, plus 4, so negative 3.6 plus 4 is 0.4. Down here in the purple, this is the point on the line which is closest to the origin. Certainly not the only way we could have done this, but it is one correct way. Okay. Create the standard form for a circle. Once again, this is something that you would have seen before, but memorizing the formula alone is not what we're trying to do. I know, because I've seen some of the previous work, I've already noted that some of you guys could tell me that this is the standard form for a circle. It's not enough to go through and say, this is the formula. You should understand where it comes from, why it works. It's the Pythagorean Theorem. Because if we are looking at the distance formula for a circle, we could take a center and draw the circle. And what we would, of course, observe is if we wanted to have the distance between the center and any point on the circle, we would once again create a right triangle. This is the point xy, a point on the circle. The center is the point hk, and so applying the Pythagorean theorem once again, this leg is x minus h, so leg squared, plus the next leg squared in the blue. This leg, as we saw with the distance formula, y2 minus y1 squared, leg squared plus leg squared equals hypotenuse squared. And for this particular drawing, the hypotenuse of this circle is just the radius. So leg squared plus leg squared equals hypotenuse squared. It's nothing but the Pythagorean theorem written in a different way. It's just the Pythagorean theorem written with the specific context of a circle. That's all. Okay, so find the equation for the unit circle. We know that this is the equation, or equals, we need to be plus sign. This is the general or standard form for a circle. Do you remember from geometry what the unit circle is? Where is the center for the unit circle? At the origin. What is the radius for the unit circle? Unit means 1. So, a definition you need to recall, the unit circle is at the center with radius of 1. I want to stress the importance of the unit circle. When we start working with trigonometry, we are going to use the unit circle a lot. It is very important to understand the unit circle for trigonometric purposes. Well, basically, all we have to do is start plugging this stuff in. The center has an x-coordinate of 0. It has a y-coordinate of 0, which gives us the h and the k. The radius is 1. Now simplify it. X minus 0, x squared. And taking what Alex told us, x squared plus y squared, and 1 squared is just 1, so voila. We have the equation for the unit circle. X squared plus y squared equals 1. This, of course, plays a significant role for us because it gives us now a general guideline for what circles look like with their equation. We saw previously that parabolas have the general form of y equals x squared. And we noted things like you could do a horizontal shift to the right 2. And we could do a vertical stretch by a factor of 3. And a vertical translation down 1 unit. But we could do algebraic manipulations on the equation and observe the effects on the equation. It will be no different here. So, progressing here. Find the equation for the circle with a radius of 4 and a center of -2, 3. Now, 2 different approaches we can look at it. We can just use the formula. That, of course, is the simplest way. Just plug it in. Well, the x-coordinate is -2, so we have x plus 2 squared. Y-coordinate is 3, so we have y minus 3. Radius is 4. 4 squared gives us 16. And so here we have the equation, or an equation for the circle, in standard form. How are you going to plug it into your calculator? We understand these graphing calculators require us to have something of the form y equals blah.
Isolate the y.
Absolutely right, you got to isolate the y. So start by subtracting over x term. From there, we could take the square root, which would leave us with y minus 3 equals square root of 16 minus x plus 2 squared. Of course, we need to add 3 then, so we would have y is equal to 3 plus this square root. And we now have something we can enter into the calculator. Okay, clear that out. 3 plus square root of 16 minus x, was x plus 2, wasn't it? X plus 2 squared, and we can graph it in our standard window. And we don't get to see a whole lot. So let's go. Okay, trying to figure out basically what went wrong, why we're not seeing much. Alright, Ryan is noting that there's a double parentheses on this particular one, which is what threw me off. So we hit delete on that one, because I had the whole thing being squared. So here's what we've got. That's still not a circle. What's wrong with it? Exactly, we've got an artifact going on. In particular, one of the issues we know we have to be careful about,
Radius
our square root is only the positive square root. We need to keep in mind that when we take the square root, it's not just positive, it's the positive or the negative square root. So we should have had positive or negative, leading us to also need the bottom half of our circle.
That's what I was thinking at first.
No, then we're definitely on the right track there for what you were thinking, Alex. So we'll come back, put this thing in. 3 minus square root 16 minus x plus 2 and gotta be squared. And then now we can hit graph. And we get the bottom half of our circle. Of course, we recognize some issues with the artifact showing these pieces are not actually connecting, though we know that they really would. We also have to remember the pixel problem that we discussed back in chapter 1. It's not a square number of pixels. Since it's not a square number of pixels, it distorts the image, which of course is why we have zoom square as an option to go through and actually fix it for us, giving us a change to create the square scale, providing what we need. Okay, one of the main skills that you will need to use from your previous work with quadratics. What circle is this? We know if we can write it in standard form, we can instantly look at it and identify the radius. We can look at it and instantly identify the center, which is all that we care about. What is the center? What is the radius? Well, if we're going to get that, we need to change it from having 2 occurrences of x down to 1. And in order to do that, we're going to need a perfect square. So we will need to complete the square on the x's. Likewise, we will need to complete the square on the y coordinate. And so we're looking and saying, what are the missing pieces? complete the square 2 times so that we could rewrite it into standard form. Well, over here in the black on the x squared, what's the missing piece? 2 squared. Take the center one of 4, cut it in half. After cutting it in half, we square it. 2 squared, of course, is 4, so we'll add that to the right-hand side to keep it balanced. Over here, -6 cut in half, as Brian noted, is -3. -3 squared is 9, so we'll add that to the right to keep it balanced. And completing the square in this way allows us to rewrite this so that it looks like x plus 2 quantity squared and y minus 3 quantity squared. And then on the right, 5 plus 4 plus 9 is 18. Thus, now that it's in standard form, we can immediately identify the center, -2, +3. We can immediately identify the radius. Please don't make the common mistake. What is the radius? It's common for students to make the error and say it's 18. It's not.
Squared.
It's not 18 squared. This piece is already of the form r squared.
So you got a square root.
So we must take the square root to get the r, to get the radius by itself. Many students will make the mistake of saying it's 18 squared or 324. Many students will make the mistake of saying it's just 18. You, of course, have to avoid those mistakes. You have to know it is already of the form r squared. You must take a square root to get it by itself. At this point, I want to pause and note. The rest of the video is about ellipses. Short version, ellipses are circles that have been stretched horizontally or stretched vertically. Imagine just taking a circle and pulling it outward or pulling it upward and stretching it almost like a rubber band. What is the effect? Basically, how do you get that with an equation? The rest of this video is going to look into that phenomenon, looking at the relationship between an ellipse's picture and its equation. We will do some problems like this where we have to create the equation for an ellipse so that we can describe it. It also requires us to complete the square. I do want to emphasize, though, circles are far more important than ellipses. Knowing the distance formula, knowing the circle formula, being able to explain where they come from, understanding that they're both the Pythagorean Theorem just rewritten, that's the important concept to work with. And now we'll move on to ellipses. Graph the unit circle in the window. Okay. Well, we know the unit circle had this equation, which means we can rewrite it. Y squared equals 1 minus x squared. So y is equal to the positive or negative square root of 1 minus x squared. Here are the two equations that we will need to plug in. So we'll come back to our equation. The positive square root of 1 minus x squared. Oops, come back. Squared. And we will have the negative square root of 1 minus x squared. We were told to graph it in the window from -1 to 1. And our y coordinate, -1, 1. And we can hit graph. Once again, we see the pixel problem where it doesn't actually look like a circle, but we're going to go with it anyway. consider the next stage. Here's our circle. And now we want to graph it in the window -1 to 1 for the x's by -2 to 2 on the y's. So we'll go and change the window. And please consider the effect. When we switch it from -2 to 2, what's going to happen to the picture? We can see right here, next to the table, what just happened. So what does it look like then? We know that by making the y values taller, it had the appearance of the overall thing being crushed downward and looking shorter. This is what ellipses do. When we look at this, we know that the calculator is using the equation for a circle, but it doesn't look like a circle. It looks like a flattened out ellipse. Our task is to figure out not just how you change a window to make it look like an ellipse, because once again, we know that this really is a circle. Based on the equations, it's a circle. But how do you manipulate the equations so that it is an actual ellipse? Consider this one. X over 2 squared plus y squared equals 1. So we're examining this equation. Well, how are we going to get the y by itself? You see the algebraic simplification I made?
Yes.
I evaluated the exponent of 2. Instead of having x over 2 inside the parentheses, I took this component and rewrote it as x squared over 2 squared, and then didn't need that stuff. Of course, 2 squared gave me the 4.
The first thing you know,
Yes. Taking the square root, we have the two things that we would need to be able to put in. 1 minus x squared over 4. And here's the big reason why I did it. The big reason why I evaluated that out and turned it into the 4 is it makes it a whole lot easier to manipulate my equation now from what I had previously. I can just come up here, take my two pieces and say x squared divided by 4. Please note that I made certain to keep the divide by 4 still in the square root. And the window we wanted was from -2 to 2 in both instances. And so here's what we see. Please note that it's on a square scale, -2 to 2 for the x, -2 to 2 for the y. Here is our ellipse. What happened to this circle, basically? We took the circle and grabbed the edges, pulled it outward, left and right, and stretched the circle from being here. The circle would have been there. We grabbed it here and here and stretched it outward like that.
Ellipse is a fancy name for an oval.
Yes, an ellipse is a fancy name for an oval. Except an oval, if you want to get really technical into it, an ellipse is going to have very special geometric properties. Ovals are just kind of like this flattened out weird looking shape that doesn't necessarily have to be a perfect ellipse. There are geometric properties specific to ellipses that ovals may not have, although basically they are very, very similar. No, but they're not quite exactly the same, but most people think of them being exact. It's not always. Okay, coming back to this part, what do you predict would be the effect? Instead of taking x over 2 plus y squared, what if we did y over 2? What would you predict is the effect? Well, in this instance,
I said coming skinny.
I've been wondering that too.
so at this stage, we'll go through, take all of these pieces, and when we take the square root, hang on, I gotta backtrack this thing. Okay, y squared over 4 equals 1 minus x squared. When we multiply by 4, we've got that. And then when we take the square root, we wind up with this. Yeah, I don't know, for some reason my brain got stupid and it was putting the square root in before I took the square root. I don't know why I was doing this, but my brain got crazy for a second. I apologize for that.
Oh, wow.
Okay, so we'll go and put this thing into our calculator now. Y equals 2 times the square root of 1 minus x squared, and negative 2 times the square root of 1 minus x squared. And we can graph it and see precisely what you predicted, Alex. Instead of having a horizontal stretch, we have a vertical stretch. Which of course gives us the main thing that we're concerned with. It gives us a way of creating the stretch. If we take the x over 2, we can make it twice as y. By taking y over 2, again, this is y over 2 before the squaring, we can make it twice as tall. Thus, we get the standard form for an ellipse, x squared over a squared, y squared over b squared, and it's going to equal 1. So, for this particular instance, A is a measurement of how much you have for a horizontal stretch. B is a measurement for how much of a vertical stretch you get. Both of those are centered at the origin. Well, what if we don't put it at the origin? What if instead of being at 0, 0, we put it at the center HK? That's not a big deal. We know how to do translations left or right. We know how to do translations up or down, just putting them on the y value. If we take it and shift it to h, we've got x minus h. And then we can also take y minus k. In this instance, I want to emphasize the minus h is a translation, just shifting the circle, shifting the unit circle left or right. Then we are taking the minus k, taking the unit circle and shifting it up or down to make the centers match. After making the centers match, we can apply the over A, which we saw has the effect of a horizontal stretch. After that, we would apply the over B, giving us the vertical stretch. So, distance formula, equation of a circle, they both come from an ellipse. It's just a unit circle with, what did this thing do? we can shift the center to HK. We had a horizontal stretch by a factor was that letter, that variable A, and that variable B is a vertical stretch. That's all an ellipse is. You take the unit circle and shift it to a different center. Stretch it out horizontally, stretch it out vertically, however much those stretches are, that gives you what you would need to create the ellipse.